It's really very nice to be here. I really like these Climath meetings, but I tend to make a mistake in terms of determining whether they're going to be mostly climate people or mostly maths people. And this talk is a little bit designed more for well, maybe it's not, but I would say it's a little bit for climate people. It's for people who are actually trying to use, well, no, some are using models too. So this is exactly the talk I want for this audience. Now, I think another title would be, this is sort of a call for better experimental design. A lot of the times when we're trying to do things, or at least we're talking about eventually trying to do things, we run models and we see what happened. And if you run a model in a 10 to 7 dimensional space, something interesting will always happen, right? But the thing is, you have to say what you're looking for to happen before you look at all these things that might actually have happened. So what questions? What do I mean by questions on the table? So here's the first one. I mean, the main point I want to get through is just, in my abstract, is just the blue. The best available model is irrelevant if it is not adequate for purpose, right? If you're trying to do mathematics, if you're trying to understand something, right, it doesn't matter. But if you're actually trying to do something, to answer a question in the world, then you need the model to be adequate for the purpose you're trying to use it. If it happens to be minimum RMSE or highest information content, that's great. But if it doesn't actually answer the question, then you probably shouldn't show it to the decision maker. So here's the question. How many reindeer hunting licenses should be issued in Utenheimen in Norway on the 1st of January, when the winter isn't over yet? Right? And this is very important because after a good winter, you can issue lots of hunting licenses, and after a bad winter, you need to offer fewer, and it's not even the end of winter yet. So what we do is we jump immediately into model land, right? So we get into model land, we build all of our stuff. We have to avoid certain deadly pockets, right? Especially this lake of self-delusion, or the perfect model, right? Because then you just become a mathematician and you're studying the model of reindeer. You're not studying reindeer anymore. So we've done this. Ed, on the first slide, has done this. And the model forecasts were horrible. I mean, they were well, some of them were good, but some of them were really bad. On the other hand, they showed why they were bad. We understood the dynamics of the system of when this model was really bad, and that gave us an idea, that told us how to actually look at the weather, right? Too complicated to model, but to look at the phenomena that led to high reindeer populations and low reindeer populations. So then the question is, was this a good model? Right? The quantitative output was horrible at first, but then it led us to understand how to talk to rangers about issuing licenses. Now, there are lots of questions like this. Might jellyfish shut down my nuclear power plant next week? Unfortunately, what they ended up doing was building a one-day deployable jellyfish protector, so they didn't need to know the answer. Right? So for the Royal Lifeguards, how often should we train in really dangerous weather conditions? They get most of their injuries when they're training in dangerous weather conditions. But if you never train in dangerous weather conditions, you don't know how the boat feels. This is a very nice flat, this is an amazingly flat sea. Right? So you need to know how the boat feels in bad weather, but how do you make that decision? Can structural model error? So here I'm really interested in structural model error, the second case from before, where the model is structurally incorrect and it's probably in a completely wrong state space. So can I learn something about that for nuclear stewardship by just dropping bombs down towers? And this is a group of us at the bottom of mineshaft UA1, I think. They were going to put a bomb here and blow it up, but they dug this hole just before the Test Ban Treaty was accepted. And the answer was yes. And then how likely is it that testing this bomb will accidentally ignite the atmosphere of the Earth and we'll all be gone? Now, that calculation was done. It's been declassified. And the lead author is Teller. And he basically said that no ignition of the atmosphere is likely to occur. So what does that mean? For the IPCC, likely is between 0 and 34%. That's sort of an odd range for multiplication. If it's 0, I'm fine. If it's 34, I'm not so happy. For the CIA, not probable is 25% plus or minus 12, so 15 to 35. I don't want to get on an airplane, much less risk the planet at that kind of thing. Later, Teller and company actually give a number. What I really want is the probability of some x in the real world conditioned on the information that I have, all the information that I have. And I take my observations and my understanding, and I plow into model world. Now, with the reindeer, we were lucky. We go into model world, we skirt this idea of optimal solution. Once you go into here, it's so much fun. You're just doing maths, you can optimize, you never come out. We never use the word optimal because it's never optimal in the real world. You couldn't even say what optimal means. We skirt the confederation of exact sentences, we find some insights, and boom, we're at the exit, and we go back over. But what we come back out with is knowledge that the reindeer depend more on a variable we can't measure or model, but we can observe it. Right? Okay, so the hope is sort of we have our understandings and our observations, and we go up and we find the probability of a model variable conditioned on I in some model set. So when the previous speaker did the Lorentz 96 Model 1, everything was in the same state space, even if the model wasn't perfect with the system. That helps a lot. And when he goes to, if the system is Lorentz 96.2 and the model is Lorentz 96.1, then there's a projection. There is no ODE. The data is no longer deterministic, right? You can't build a model in Lorentz 91 space that actually reproduces Lorentz 96.2. And that means that you can't do UQ inside model land, which I think is on the next slide. Right? We actually have to somehow stay in here long enough to try and push back out and get models and insight. Oh, yeah, this is important. This is only a model of model land. It's not the actual model land, so there may be some limitations on the conclusions you can draw. When we want to do UQ, the vast amount of UQ is done in model land. A lot of the problems are that XM is not X, right? So if you look, if you look in the questions governments submitted to the IPCC, several of them, including the Netherlands, say, please always distinguish between a model land variable and a real world variable. We'll see how they respond to that. And there's a paper just out with Jim Berger and I trying to talk about this. What we really need is to also quantify the probability of a big surprise, meaning the model fails utterly. Something happens that the model couldn't do even in retrospect. You cannot shadow. These are the things that cause these things cause large disasters. And we have to figure out, we'd like to figure out a way to see them. We confuse model diversity with our own uncertainty. In this case, this was shown on the Weather Channel, and those yellow lines are different paths. They didn't have the cone here, I don't know why. But this is my brother's car. So I'm from Jacksonville, right over here on the coast. And this graphic wasn't giving the information people over here or over here actually needed. So again, there's this question of communicating. This is communication in model land that was supposed to be relevant in the real world. Again, traditional UQ sits there. Okay, so for those of you who are still awake, I want to ask a question. You have 3 options. You can read them. So for a show of hands, how many of you would want to provide useful information to the rangers on reindeer? Is that really your goal? Well, that's a shame because that's our goal. Right? I want to tell people about heat waves. I want to talk about various probabilities of real things happening in the real world. I think the IPCC should be, well, I think all reports, I'm not picking on the IPCC, should be more addressed to policymakers. Right? They need probabilities in the real world. And the IPCC has gotten much better on this. They take 30-odd% of the central probability and they throw it into the tails for global mean temperature. And that's to express the probability of a big surprise. But again, many of the rangers are basically being hand-fed one model run on, one model run to 2100 without consideration that there's a good chance it will be outside the range of the models. Oops. Do you want to explore the properties of your new reindeer forecast model? Some of you don't want to do anything, or maybe you're just asleep. So this is a completely valid thing. I'm not trying to forecast yet. I mean, I don't want to forecast with that model. I just want to understand how can I forecast, how can I build a model that will eventually be a better forecast? As long as I don't claim my forecast, so they may be the best available, but if they're not adequate, that's a fine thing to do as long as I'm just developing the model. And many people, right, they're actually aiming to sell your model, especially now, big companies, to sell the model to the Norwegian government or to secure a grant. Right? Okay, so I'm afraid the conclusion is there are only 7 people still awake. Okay, so let's take 2 examples with less reputational risks. Right? So sometimes you talk about things that people really are going for money on. It's just you get very defensive arguments. So I want to have as many probability forecasts of a similar nature that I can. The events happen often, say a dozen of a week. Everything is probabilistic, and lots of different forecasts are competing. I have a great one. It's forecasting the probability of each team winning this weekend in the National Football League, American football. This has already been set up by 538, so all you have to do is drag the little dot. These are my forecasts for last week. 538 says probability is in there, and you can see where mine fell. And 12,000 people play this game, right? So you get a leaderboard, which is the highest people, where the actual points they have week 10 are really spread out. They're only like 3 across 700s, right? And you have the middle. I think I don't have the middle anymore. The middle's gone. They're very close together. No, this is the middle, around 50%, right? And there are many, many people in the same group. And then at the bottom, the negative scores are like minus 5,000. The highest score is like 700. So there are actually a zillion really interesting questions to ask about how this goes and how you actually try to maintain your position. This is last Sunday. The games weren't finished yet. That's what the live are for. But I took the picture because I didn't think Du or Ed would believe that I actually made it into the 99th percentile, the top percentile. I didn't believe it, actually. I'm usually behind Ed and Du. It was actually okay. At the end of the week, I'm still up there. This was the worst performance I've ever had, and yet I moved up. And that's just you have very counterintuitive, the questions you're trying to ask often lead to very counterintuitive outcomes. This is one I'd really like to talk about but don't have time. This is trying to estimate the probability of winning a function of the time in the game. And you get these completely unreasonable, jumping from 16% to 80%, down to 40%, up to 99%. How do you evaluate a mission like this? It doesn't have to be a football game. Right? How do you actually even evaluate this evolution of probability in time? I can game this, right? We have some scores that show that this is not a good, it's hard to find anything this would be good for. But if you had a question, how would you actually do it? So again, things aren't horrible, right? This is not a sad song. This is Jim Hansen, Rhodes Scholar, PhD student of mine from Oxford. He won the Navy's highest civilian award for a probabilistic pirate prediction service. Right? This is real pirates with the Navy. I mean, and of course, it all went behind the fence before it was finished. So I don't know what it actually does anymore. But I mean, that's the point. It's actually valuable information. And it's by backing off and trying to see what we can do that's adequate, talking to the people who are using it, rather than trying to find something like a perfect model. Paul Teller, son of the famous scientist, he actually has a paper called Twilight of the Perfect Model, where he suggests that in all of physics, we get away from this perfect model, right? That we're trying to build a perfect model and move back to things that are more obtainable. This is another one. We call these the Stark sticks. This is my pair. And lots of data. We were trying to figure out exactly, there are lots of questions you can ask, right? How long is it going to take for the long stick to go over the top? How long is it going to take? How many swings will it be before the long stick goes over the top? How many times will the long stick go over the top in the next 5 minutes? So that was too much for Tony Stark, unfortunately, who ended up grabbing these things and throwing them in the trash can in this scene in the movie. But given the system in a detailed time series of observations, the first thing a statistician does is to compute some function of the time series, right? Under the same conditions, the first thing a physicist does is to take the batteries out. When I take the batteries out, I can compute lots of things about the free motion of these sticks, which then give me parameters that it would be very difficult to work out while the thing's spinning around in its little chaotic motion. But sometimes it's just such a cool little device once you actually start taking this was the night before another talk, taking lots of other data, that you just get so caught up in taking data and seeing what you can see that you don't think so carefully about that. This work is being done by Du, who's building statistical models, and Richard Bauer, who's obviously a cosmologist from the background in this picture, who believes that he can use Mathematica and integrate. He can find the real equations. I'm not sure there are real equations. Right? It comes back to this question of, do you believe the laws of physics describe the thing we're looking at? Or do you believe that they govern the things we're looking at? And as Michael said earlier on the first day, there are issues that we can't know. Eventually, it's got to be stochastic because there's stuff coming in from outside what we can currently see in terms of our light cone, right, which is going to affect the system. What I'm really trying to get across is that the model class you draw from and the PDFs you make vary with the question asked, and very often the words on the degree you hold. When you go to industry and ask them about extreme events on decommissioning nuclear power plants, they'll actually hire several different people to do the analysis. And sometimes they get answers which just don't make sense, right? Like one plant has the expected time until this event is 30 years. The plant right next to it, the expected time is longer or is less. Anyway, right? You've got two plants right next to it, and the time scales on which some event that they're worried about to happen it just can't be the way that it comes out. And then also, as I mentioned before, Tony Stark, the impacts this has can be big because the nuclear industry is required to go with the worst scenario. So what if you get 4 or 5 scenarios and one of them is stupid worst? So they sort of have to respect that, even if they learn why. So Tony Stark panics here in the next scene. He grabs the sticks and he throws them in a trash can. Well, what would Bruce Banner have done? Right? I mean, given the negative implications of Bruce Banner panicking, how would he have handled the situation? Now, we don't have to stay with these toy models. This is Erica. We're working with START, and this is an anticipative disaster risk reduction program. So we're looking for heat waves before they happen. Okay? By going before they happen, we can actually get supplies in before the runways turn to mud. We can take action, and we can make much more effective use of a set number of dollars than waiting for having pictures you can use on television to raise money. Okay? This one worked. We actually looked and found that the models, the American model, gave enough information on the timescales we were interested in that they were happy enough to make decisions with this. In other cases, it doesn't work. ECMWF doesn't work, and in those cases, they only have 72 hours from the time that they get the question until they fund or don't fund. Right? They have a very short period. And in cases where the model, it may be the best model, but if it doesn't inform this question, they don't want to see it. They have too many other things to do. They can just use climatology. And then there are many other such questions. So in this case, we can determine, we were worried about whether where and when the singular vectors or the Lyapunov vectors yield a better forecast for ensemble. This was 1999. We can determine if ECMWF singular vectors was internally consistent. So a lot of the work we do when we're moving into big models is we actually determine internal consistency. This makes us very popular with the customer, but not so popular with the forecasting center. As it turns out, the singular vectors, the operational singular vectors, were going nonlinear in 24 hours, whereas they were optimized over 48 hours. So whatever they were sampling wasn't what they thought they were sampling. And then what happens next, right? Do you wait for the next model revision? Do they change it? Do they continue to check it? So a lot of people picked up the method, but I don't know how many people, they see that it doesn't work, but is that what you changed today? We can actually look at structural model error and the ECMWF. In fact, what we were looking for, this was with Tim Palmer, David Arell, another Oxford student. We were interested in weakly constrained methods, right? And weakly constrained variational methods. And the assumptions you put in is that the noise is white, that is IID, almost always. And here we showed a long time ago, like 2001, that it's not white. It has a memory of about 3 days. Okay, so you can actually, you were talking about just improving the forecast. So we could improve ECMWF's forecast by adding on a historically weighted model error term, but it wasn't physical. How does that go? What do you want to do? So let me summarize. Oh, first of all, this is not a depressing talk. The Bank of England invited us to give a similar talk, Erica and I, at the Treasury, and this person tweeted a lot, but the point isn't about abandoning models, but filling the gaps between the models and reality. It's figuring out how to come back from model land to say useful things about reality, right? So it's not a sad song, right? Except, if you're really interested in building perpetual motion machines, even though you know it's impossible to build a perpetual motion machine, then you can stay in model land and just report the results of X model as if it had something to do with X real world, right? I think that's, you can't do that, and so in that case it is depressing. So the summary. It ain't the model, it's the notions. The aim isn't the model you use so much as the way you think about it. The notions that the model gives you, like the really important thing with the reindeer is whether or not it gets warm and cold and warm and cold and warm and cold, forming an ice layer that young reindeer can't get through. It's not a question about the statistics that were going into that actual model. Actually, I was really surprised. The Wiktionary has a great translation of this, saying the tools you use to accomplish a goal are not as important as how you use them. And except for the fact that it assumes that you can accomplish the goal, right, we need to find accomplishable goals that we can then apply the tools we actually have. The second one is, and if you can't run the model you'd love, right, high resolution, 2100, run the model you got. Now, this one doesn't really quite work, right? It's informative, but in fact, the model you got may not be adequate for purpose. So you can only run it if it's adequate for purpose, and that basically makes this something to remember not to do, right? You don't, if you're just doing model development and you're not going to show these results to a policy or decision maker, there's no limits on pure science. It's when the pure science is motivated by that it's going to support decision makers this year or next year that we begin to undermine the credibility of science for policy. And this is already happening. And what do you do? So EDF, Electricité de France, calls you in and asks you to evaluate forecasts for the hottest day and the wettest day on a 5-kilometer grid, PDFs, for 2095. I mean, does anyone serious believe that we can get probability distributions that are at all relevant for 2095 on a 5-kilometer grid in England? So I won't ask for hands this time. But I find this unlikely. And so does the IPCC, right? So for global mean temperature. So that's where I'd like to stop. I'd really hope we have a little time for questions. I think the real idea is to try and get out of model land early and often, especially if you're still young, and really feel the risk, really feel what it's like to have the risk out there. Or you can become a pure mathematician. So again, there's nothing I'm saying that doesn't mean you can't stay in model land because that's where you're working, right? There was a little glitch, there's a little mouth in that exit, right? That's for number theory. Number theory actually has a really easy way. If you're dealing with integers, it's not so hard to go between the real world and model land. If you want to stay in model land and study a particular kind of PDE, I'm not making any complaint about that. The issues are much more when we're doing things that don't actually address the questions that other people, that we are interested in or other people are interested in. Thank you very much.
All right. Okay then.
So I'm not 100% sure I fully understood the full message, but of course it's very important that scientists should follow their own intuition and are not always led by the big questions, right? And so you can do very useful things without working directly with an operational weather forecast or trying to do the predictability, the things that you said, right? Predicting something, whatever.
So
and not being a mathematician, right?
So I agree completely with this. That's the point. We're not abandoning models. If you're going to stay in model land, if your interest is in doing mathematics, as long as you don't say you're going to determine the best ensemble scheme, as long as you don't say something about the real world, it's completely okay. Right? It's only when you say you're going to go outside and then you stay.
I agree. So I agree. So IPCC should stop, right? We should start working 10 years on improving all this stuff, and only then we're going to do it again. I fully agree with that.
Thank you.
So it was very nice, like very inspiring. I think that everybody agree on the fact that we would like to do uncertainty quantification beyond the model land. I think we all agree on that. The point, and actually I think that this is what we used to call representativity error, which is essentially at the very start, the way how we project this unknown truth on the way we consider our model. But it's very difficult to do that. It's very difficult to quantify. So do you have any thoughts besides, recognizing how important it is?
So I think it's largely due to, I think we have to rely on expert judgment and actually understanding the system. So when Michael was young, everyone was trying to understand the system. And I find that most people are trying to understand the model. So if we go back and try to understand the system, and then expert judgment comes into play. So when the Siam Journal of UQ came out, they decided, so Jim was there, they decided to sort of see where it went. And most of the papers that came in were doing UQ in model land, right? And they didn't say it that way, but they were doing UQ in the equations that they were studying. And I don't remember the percentage, but when we started working on our paper, a large percentage of the papers in Siam UQ were in fact in. Now, this audience is very different. If this was an audience of people making probabilistic climate predictions, it would be a very different reply, which is why I give the football analogy. They don't get angry about that. But it's hard, and I think the way to do it is to try to understand the system and think of what could happen that my model couldn't do. Think of what big things could happen where my model could not shadow the actual observations, even after the fact. So for about 10 years, I've been asking, okay, in 2099, we'll actually know global mean temperature, and we'll know volcanoes and stuff. Can HADCM3 shadow that record? Do you think HADCM3, with all that hindsight, could actually do what the world does? And very few meteorologists after a pint or two, climate scientists, after a pint or two, will go beyond 50% at 2050. 50% failure. There'll be a big surprise that the model cannot do, but it will be obvious when we see it, right? And the only people who don't have numbers like 50% are Trump's EPA, but their number could go up, they said it was lower than 10%. That's still enough to act, right? They didn't say it was zero. And people who work for one particular Met Office or center. And they think the model is able to do these things. And the communication is really important because that, what is the consensus, right? So you have to worry about how these things are perceived. But on the other hand, if you keep saying things which are simply not true, eventually the credibility of the entire regime is going to go down, right? It's not, these guys lied, everybody's lying, there's a conspiracy. So no. But You know, I think it's important to be very clear about what we think we can and can't do. Expert judgment can do that. I guess the last comment would be, so Jim Berger did the hazard maps for Montserrat, a volcano, and where things would happen. 5 years, 6 years after that study, they had 7 1 in 10,000 year events. So, I mean, he's a Bayesian, right? The Bayesians have to expect this. So he went back and he looked at the model, and they had a really nasty ground coefficient of friction for pyroclastic flow. And they realized where did it come from, why it was physically wrong. They measured it again, and they got rid of all but one of those 1 in 10,000 year events. Right? But does he really believe that was the last bug in the model? It's tricky. So that's another case of where, if you think about it, you can figure out what the physical cause was. We have a paper out called the relevant RDU, relevant dominant uncertainty, the airport where Jim lives. And that's just trying to figure out, in this model, where is the weakest point? And physically, what could happen there?
Because it's specific. Mine is specific.
One last question from Valeria.
Yes, actually, to a specific example, you provided, the one on heat waves in Pakistan. So a PhD student of mine studied the bias between the extreme events in terms of heat waves of reanalysis, as represented by reanalysis, versus station observation, and the difference is more than 3 degrees on the extreme events. So even the statistics is wrong by an amount that's very large with respect to the idea of calling a heat wave or not. Even if you do bias correction up to first and second moment, you still don't get the heat waves right, because the model misses the asymptotic property of extreme value loss statistics. So this is an example which fits very well to what you're describing, where the model is extremely well formulated. By the way, the average is perfectly captured, okay, or very well captured. The model just misses, is unable to answer the specific and relevant question you want to ask. So I will send you this.
That's right. No, I think the style of work that you do is so there's a style of work that looks much more general. Can we have Michael's question? There's a style of work which works much more generally, and it tells us more general things. It doesn't give us 5-kilometer probability distributions for the hottest day in 2027, right? And that work can show us things we can't do. And that's why, again, with Peter's comment, there's an issue of not constraining modeling, but also not selling the best available model when you're sure it's not adequate for purpose. And it's somehow, I don't know how science managed to do it, maybe it never did, but now that it's so much more in the public eye, I think it's important to investigate, so why? Why is that the case? Without trying to say, I'm going to give you the wettest day in a 5-kilometer square around my Oxford College.
Well, it's always an exquisite pleasure to listen to Lenny, holding forth out of model land. I really want to give another example of this sort of thing. Please understand that I believe that it's getting warmer and that we're contributing to it and that we should do something about it. But, my son, who is a great enthusiast of the environment and so on, really came up excited after the special report of the IPCC on sea level rise. No, sorry, on the 1.5 versus 2 degrees. And then I looked on what was on television. It said 1.5 will be sea level rise, 75 centimeters, 0.3. And 2 degrees is going to be 1.1 meter and 0.7 centimeters, etc. The numbers might not be exact, but there were 3 digits. And we know that the uncertainty in global temperatures is, from 1.5 to 4.5, etc. So that is such an example. In first course in engineering and statistics, they tell you not, or in measurement, is not to confuse precision with accuracy. So
no, I think that's a great example. So I go to Climate Science Day in the U.S. Any of you who have a U.S. connection, I recommend you do it. For the last 5 years, I only go. We spend 2 days going to offices, to individual senators and House members, and in the U.S. report, in the Florida Southeast section, there's a graph just like you described. It's working hours lost by state. I mean, the little dots everywhere, and we can't know this. And there's even a note, in the footnote it says, note these results depend on economic models which are not always accurate. I can't remember what it says. It doesn't mention that we don't have the others. I show a graph that shows, from the same report, that shows the percentage of marsh, what I grew up in, so salt marsh, and the percentage of mangrove as a function of the temperature. You know, they look at that. They know what salt marsh is, and they know what mangroves are, and it completely changes what lives in the sea outside. And they see as the temperature rises, the mangroves coming up the side of the coast. They don't want that. So, and that's nothing about the future. That's just saying in this temperature it is observed. This is the coastline you get. So this is something that actually tells them something. And all we need to know is very vague information about rising sea level. So it's moving more towards that and less towards these other graphs, which sometimes I can't even figure out how to read them.
Thank you very much.
Thank you.